Recently, my homepage has been flooded with AI videos explaining RAM, and what drives me absolutely crazy is that they're not only AI generated but also completely incorrect. These videos take advantage of beginners, feeding them straight up garbage. So I've taken it upon myself to explain every DDR RAM generation correctly, and by the end, you'll know more about computer memory than 99% of the planet. DDR1. Before DDR RAM was introduced in '98, personal computers used something called SD-RAM, but SD-RAM had a big problem. It was not using its full potential. You probably know that computers use this thing called the clock speed, a frequency that's used to synchronize the operations of its components. We can represent it visually like this, a line with rising and falling edges separated by the same length of time. The problem with SD-RAM was it only used the rising edges of the frequency to send data, and you don't have to be Einstein to figure out this is not super efficient because it basically ignores every other signal, aka the falling edge. DDR, on the other hand, utilizes both the rising and the falling edge of the same signal to send the data. So if the module had a base clock of 200 MHz, it would double its output to 400 megatransfers per second, hence the name double data rate. As for the original SD-RAM, people started getting super confused because DDR is technically also a type of SD-RAM. So they changed its name to Single Data Rate SD-RAM, or SDR. This is basically the same retcon World War I had once the sequel dropped. Originally, it was just called The War to End All Wars, but we all know how that ended. DDR2 worked similarly to DDR1. It had all the same tech from the previous generation, but built on it further. Instead of increasing the base clock speed, it simply doubled the amount of data it sent. While DDR1 sent 2 bits of information through one of those pins on the bottom of the RAM stick, DDR2 sent 4 bits through each pin per clock cycle. But this created a different kind of problem. Think of data as water, and those tiny wires and circuit pads on a stick of RAM as pipes. You can't just increase the amount of water you send without increasing the water pressure, aka the speed at which you can send data. It would create a sort of traffic jam, and it wouldn't matter that you sent more data if it didn't get there in time. You see, back on DDR1, the same base clock signal was used for controlling the reading and writing of data on the memory cells and for controlling the input-output bus that sends data in and out of the stick. On DDR2, engineers separated that signal into 2 separate ones and doubled the speed of the frequency that controls the input-output bus, effectively getting rid of the bottleneck. It's also worth mentioning that this input-output frequency is the signal that is being doubled by the DDR, not the base clock speed that reads and writes data into memory cells. Aside from this optimization, DDR2 sticks had a differently placed notch compared to DDR1, so you couldn't accidentally place the wrong type of RAM into your motherboard. This notch system wasn't new to DDR2 but continued with every new generation of DDR memory. DDR3. This generation was pretty boring at first glance. It basically just doubled the prefetch and IO bus speeds again, from 4 bits per pin to 8 bits this time. Other than that, DDR3's biggest upgrade might be the flyby topology. On DDR2, the signal traces branched out to all chips at once, like a fork in the road. The goal was to make sure the signal arrived at every chip at the exact same time, so engineers had to make sure every branch of the fork was the exact same length. This layout was messy and created electrical noise that limited speed. DDR3 fixed this with flyby topology. Instead of branching, the signal travels in one clean line, visiting each chip like a train stopping at stations. This made the signal way more stable, but it did force the memory controller to become a kind of conductor, timing the data so that even though the chips were at different points on the track, they all stayed in perfect sync. DDR4. While previous generations relied on more brute force methods to increase transfer speeds, DDR4 focused on efficiency. It kept DDR3's 8-bit prefetch but reorganized the module's layout. One of the most impactful changes was organizing memory banks into bank groups. You can think of memory banks as logical segments of memory chips, those black squares on a stick of RAM that actually store data. On DDR3, all banks were connected to a single internal data lane. The problem with this layout was that the CPU could only talk to one bank at a time. Since all these banks shared the same path, the CPU couldn't ask for more data from other banks until the first one finished sending its own data. This created dead air in the input-output buffer, the waiting room from where data is sent to your CPU. DDR4 solved this by giving these banks separate internal lanes through the concept of bank groups. With 16 banks organized into 4 groups, the RAM could now tag team the data flow. While Group A is recharging, Group B is already sending data down its own private lane. This keeps the input-output buffer constantly full. And because the buffer was never empty, engineers could finally double the input-output bus signal speed and reach 3200 megatransfers per second. Also, you might have noticed I've been using megatransfers per second instead of megahertz when talking about max RAM speeds. That's because, and I hate to break this to you, RAM speed is measured in megatransfers per second, not megahertz. Only the base clock is labeled in megahertz. So every time you see 3200 megahertz RAM online, that's technically incorrect. It's 3200 megatransfers per second. For some dumb reason, the megahertz label stuck, and for the last decade, we have all been fed false advertising. DDR4 dominated for about 7 years and is still widely used today, as many haven't transitioned to DDR5 yet. Matter of fact, I myself am still using DDR4 RAM, partially because I'm broke AF and partially because I hate DDR5. And finally, we have DDR5. After skipping a generation, they finally doubled the prefetch again to 16 bits per pin. But here's the twist: DDR5 actually splits each module into two independent 32-bit channels instead of one 64-bit channel. This means your motherboard can talk to both halves of the stick simultaneously. This is basically the same principle as DDR4's bank groups. The goal here is to reduce dead air by making one half of the stick independent from the other. Basically like dual channel, but on one stick level, kind of. You still need two physical sticks in alternating slots for actual dual channel. DDR5's internal split doesn't replace that, so don't place two sticks next to each other. DDR5 is also the first generation to introduce on-die ECC, to consumer RAM modules. ECC, or error correcting code, is basically just a chip that corrects flipped bits that happen because the memory cells are now so tiny and dense. This tech is particularly important in servers and, of course, AI data centers. I'd like to point out how hilariously ironic it is that the same DDR5 modules that run AI data centers create these AI slap videos just to explain their own architecture incorrectly to people online. Just more the reason for you to actually read and don't rely on AI for everything. So I encourage you to go and read the DDR Wikipedia page and correct me if I made any mistakes, because that is the whole damn point.